branching at different places. So if you have a if you have a case like this, then you have to have the branching over here is B1, branching over here is B2. So capital B will be B1 into B2. And the gate F4, G1, G2, G3, G4, that will be the capital G, G1, G2, G3, G4. Similarly, H, if you have, this is the input point and this is the output point. Here the capacitance is C out and here the capacitance is C in. So H is given by C out by C in. Now this we can process by looking at the network. We know the NAND gate, there G is given by N by 2 by 3 and NAND, N input NAND and N input NOR is given by 2N plus 1 by 3. And inverter is 1. So looking at the gates, we can compute this G over here. Looking at the netlist, the branching, we can calculate B. And this capacitance and this capacitance are given, you can estimate by parasitic extraction. So you can calculate this. So now you have the expression for the path F4 of the logical network. So now we are not talking about a single gate. We are not trying to find out the delay over here. Then it is very easy. We have seen that. But we are trying to find out the delay through all these stages from here to here. So we need to compute this as G, B, H. Then our goal will be to basically distribute the F4, F1, F2, F3, F4 equally. So we'll try to make F1 equal to F2 equal to F3 equal to F4. And that will be equal to F to the power 1 by 4. The idea is that if I do this, then my delay is minimum. In that case, the delay is equal to M. M is the number of stages multiplied by F. F is equal to or let's write N because we are just showing over here F to the power 1 by N. N is the number of stages plus the parasitic delay of this one, P1, P2, P3, P4 plus the sigma I Pi on the path. We are not interested in this or the other one. On the path of the signal, whatever the gates are, they are parasitic delay. The sum of that, we put that. So this is how we calculate the delay are you going to do that? So this is how to do that actually. And this is very much required because you don't waste time when you're working in a big company, because at the end of the year, your performance will be evaluated by your superiors, and if the company is having some bad time, not now, but they go through ups and downs, then your job will be in jeopardy. So you'll have to invest your effort in a very smart way. So how do you do that? You just cannot sit in front of the computer and make 10 different design of a decoder or 10 different design of a particular adder. You have to manually estimate the delay of the different options. And then you decide which option is better than others, looking at the pros and cons. So you narrow down to 2 or 3. And then probably within the 2 and 3, you further look at that whether to develop. Because this does not account for the interconnect delay. You understand? This does not account for the interconnect delay. So if I have a adder, which we'll talk about later, which requires long interconnect, obviously that's going to slow down when you actually fabricate it. So as an engineer, you'll have to apply those extraneous parameters in the optimization process. So interconnect delay is not included here. Another thing is that, what else is not included here? Anybody? Now that the temperature is 50 degrees, so you should be able to think, right? I mean, it's now at 0 degree, what, minus 17 degree or whatever it was. What is the worst temperature you had?
Minus 30, I guess.
Minus 30, okay. I stopped thinking. Okay, so tell me, what else is missing here in this simplistic approach? Just think what you do in SPICE and what you're doing here. Wiring delay, well, we talked about. That is one of the things. What else? No, we are not bothered about power right now. We are just talking about delay. We'll get in there. I mean, you are ahead of time, but we'll get in there. What else? Any idea?
Elmore delay? Elmore delay?
What's the delay?
Elmore?
Elmore delay. Well, I mean, we are trying to estimate the delay in one way or another. No, that's not the reason. You remember that we talked about when we drew the schematic of the two-input NAND gate. What did you do? What's that? Huh? No, sizing, we'll come to that. Actually, that's part of the goal of that. We'll find out the sizing. What we are missing.
Is it internal nodes?
Exactly. We are not taking into consideration of the charge sharing between the C out over here and the internal nodes. Correct? So, there are limitations. If you are talking about 4-input NAND gate, so you have lots of internal nodes. So that slows down further. We are not taking into consideration lots of things because you cannot put the cart before the horse. When you are talking about a large design, you will have to simplify your model. You have to create some amount of abstraction so that you can solve the problem in 90% of the case, and the 10% of the case, because of this internal node capacitance and so on, that will be only a 10%, okay? So later on you go back and use SPICE and then try to take care of that and find out the better one. Is this clear? Why logical effort is important? So simple math. I don't want to spend much time on this type of Mickey Mouse algebraic stuff. So all it is telling us that if you have two different stages, the delay between this and this will be minimized if the delay of this equal to delay of that. So if this gate has logical effort G1 and this is G2, even though this is inverter, they will be same, but just assume that they're arbitrary gates, then G1 into H1 plus the parasitic delay B1 of this gate, just if this, assume that this is an arbitrary gate of logical effort G and G1 and the parasitic value of delay B1, and this is G2 and P2. Then the delay from here to here is given by this expression. And then we substitute H2 by H by H1, and then we do differentiation to find out basically what we talked about here, that F1, F2, F3, F4, all those things should be equal. So that's what this particular slide showing, that we get the optimal delay when every stage has the same amount of delay. So having said that,